Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the area of this circle that is inside square ABCD. And in the second question, we will find out the value of the green area that is inside a quarter circle. So we start with the first question. In the drawing, we have a square ABCD. Inside square ABCD, we have a circle. It's given us the question that angle CBT, this angle equals to 30 degrees. And we also know that line segment PD equals to 5 units. And our mission is to find out the area of this circle. Okay, so first of all, we will define the center of the circle as O. We will join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle that we will define as R. And we have here the radius OP that is drawn to the point of tendency. Therefore, according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. This angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we join points O and Q together by a straight line. Point O is the center of the circle, point Q is the point of the circle itself. Therefore, OQ is the radius of the circle that we define as R. We have the radius OQ that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. We know that all the angles inside the square are right angles, so this angle equals to 90 degrees. This angle will be also equal to 90 degrees. This angle equals to 90 degrees, and finally this angle will be also equal to 90 degrees. For square ABCD, all the angles inside square ABCD are right angles. So here inside quadrilateral OPQN, inside this quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees plus the size of the fourth angle. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the size of the fourth angle must be equal to 90 degrees because of the fact that 270 degrees plus 90 degrees is 360 degrees. So in order to complete the sum of the angles in this quadrilateral to 360 degrees, this angle must be equal to 90 degrees. So So actually we found out that inside quadrilateral OPQN we have 4 right angles. Therefore, quadrilateral OPQN is a rectangle. I'll write it down. Quadrilateral OPQN is a rectangle because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, PO equals to NQ. PO equals to NQ. But we have already found out that PO equals to R, so I can write here that PO equals to R. And from this equation, R equals to PO equals to NQ, we will derive that NQ is also equals to R. Here NQ equals to R. Likewise, according to the same rule, that the opposite sides of a rectangle are equal to each other, we get that side OQ equals to side PN. OQ equals to PN. But we already found out that OQ equals to R. And for this equation, R equals to OQ equals to PN, we will derive that PN is also equals to R. PN equals to R. PN equals to R. PN equals to R. So we actually found out that quadrilateral PONQ is a square. Why? Because all of its sides are equal to each other, they are equal to R. Quadrilateral PONQ is a square. Okay, we also know that all the sides of a square are equal to each other. That is to say, here side AD must be equal to side AB in square ABCD. AD is equal to AB in square ABCD. Okay. We do it again. In square ABCD, all of its sides are equal to each other. That is to say, AD equals to AB. What is the value of AD? It is very easy to see from the drawing that AD equals to R plus 5. Again, AD equals to R plus 5. And it is equal to AB. What is the value of AB? AB equals to R plus QB. Again, AB equals to R plus QB. In total, we found out that R plus 5 equals to R plus QB. Here we subtract R from this equation, and we get that 5 equals to QB, or QB equals to 5. So we found out that QB equals to 5, so we can write here that QB equals to 5. Okay. In the next step, I'll present to you rule number 2. According to rule number 2, the lengths of two tangents from a common extreme point to a circle are equal. We have the common extreme point, point P. From the common extreme point, point P, we have tangent PA and tangent PB to this circle. And according to rule number 2, the lengths of two tangents are equal to each other. That is to say, PA equals to PB. So we can actually implement rule number 2 in our drawing. So if we focus at the common extreme point, point B, if we focus on the common extreme point, point B, this point, from the common extreme point, point B, we have two tangents to this circle, tangent BQ and tangent BS. According to rule number 2, they are equal to each other. Repeat again, if we focus on the common extreme point, point B, BQ equals to BS according to rule number 2. But we have already found out that BQ equals to 5 units. So we can write here that BQ equals to 5. And from this equation, 5 equals to BQ equals to BS. We will derive that BS is also equals to 5. BS equals to 5. Here we can write that BS equals to 5 units. BS equals to 5 units. What is the size of angle QBS? What is the size of this angle? What is the size of this angle? Angle QBS. You know that angle ABC, this angle equals to 90 degrees. This angle equals to 30 degrees. Therefore, the size of this angle must be equal to 90 degrees minus 30 degrees, that is 60 degrees. Okay, so in the next step, we'll join points Q and S together by a straight line. So here, by joining points Q and S by a straight line, we created here triangle QBS. In triangle QBS, side QB equals to side BS. They are both equal to 5 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle, there are equal angles. So those two angles that are located in front of equal sides must be equal to each other. So if we define one angle as alpha, then this angle must be also equal to alpha because of the fact that those two angles are equal to each other. Okay? Because they are located in front of equal sides. So we know that this angle equals to 60 degrees. Therefore, the rest other two angles, they must be equal in total to 180 degrees minus 60 degrees, that is 120 degrees. That is to say, alpha plus alpha in total, they must be equal to 120 degrees. I'll write it down. I found out that in triangle QBS, alpha plus alpha must be equal to 120 degrees. Alpha plus alpha is 2 alpha, that is equal to 120 degrees. Here we divide this equation by 2 and we get that alpha equals to 120 degrees over 2 is 60 degrees. So I found out that angle alpha equals to 60 degrees, so we can substitute here angle alpha by 60 degrees. And here we'll also substitute angle alpha by 60 degrees. So we actually found out that inside triangle QBS we have three angles that are all equal to 60 degrees. Therefore, triangle QBS is an equilateral triangle. Okay, so I write it down. Triangle QBS is an equilateral triangle. Because it has three angles that are all equal to 60 degrees. Okay, triangle QBS is an equilateral triangle, and we know that in equilateral triangle all of its sides are equal to each other. So here QB equals to 5, BS also equals to 5, therefore the missing side QS must be also equal to 5. So I found out that QS equals to 5. In the next step, we will join points O and S together by a straight line. Point O is the center of the circle. Point S is the point of the circle itself, therefore OS is the radius of the circle that is equal to R. In the next step, I will copy quadrilateral OSBQ in a new page and we will analyze quadrilateral QOSB. Here we have the radius OS that is going to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Okay, so this angle is a right angle. So this is quadrilateral QBOS that I copied from the original drawing. We know that the sum of the angles in any quadrilateral is equal to 360 degrees. So 360 degrees minus the sum of those three angles must be equal to the size of the missing angle. That is to say, 360 degrees minus 90 degrees minus 90 degrees minus 60 degrees must be equal to the side of this angle. That is actually angle QOS. So here 90 degrees minus 90 degrees is 120 degrees, 180 degrees, 180 degrees minus 60 degrees is 240 degrees, so 360 degrees minus 240 degrees, it is equal to 120 degrees. So we found out that the missing angle QOS, is equal to 120 degrees. So I write it down here, this angle equals to 120 degrees. So here, the missing angle here equals to 120 degrees. In the next step, I will present to you the law of cosines, and we'll implement the law of cosines in this great triangle QOS. So what is the law of cosines? The law of cosines is true in any triangle. So if we have a triangle ABC that could be any triangle, this is triangle ABC. And we know that the length of side AB is A units. The length of side AC is B units, and side BC equals to C units in its length, and the angle between side AB and side AC is theta. Then, according to the law of cosines, we will get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Now repeat again, in the right triangle ABC, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Actually, we can implement the law of cosines in the green triangle QOS. So I copy the green triangle QOS in this new page, and we'll implement the law of cosines in this triangle. So this is triangle QS that I copied from the original drawing. According to the law of cosines, 5 squared equals to r squared plus r squared minus 2 times r times cosine 120 degrees. Okay, this equation is the implementation of the law of cosines in triangle QOS. Okay, 5 squared is 25. That is equal to r squared plus r squared is 2r squared minus 2 times r is minus 2r squared, and cosine 120 degrees, it is equal to minus 1/2. So here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and we have here minus times minus is plus. So in conclusion, we found out that according to the law of cosines, 25 equals to 2r squared plus r squared. That is to say, 25 equals to 2r squared plus r squared is 3r squared. Here we'll divide this equation by 3 and we get that r squared equals to 25 over 3. Found out that r squared equals to 25 over 3. And we know that the area of any circle equals to pi r squared. So the area of our circle, the formula for the area of the circle is pi r squared. But we have already found out that r squared equals to 25 over 3, therefore we can substitute r squared in this formula by 25 over 3, and we get that the area of the circle will be equal to pi times r squared is 25 over 3. So in conclusion, we found out that the area that we are looking for, the area of our circle that is inside square ABCD, it is equal to either 25 pi over 3 square units, 25 pi over 3 square units, or in terms of numbers, it is equal to 26.18 square units. Okay, I'll repeat again. We found out that the area of this circle that is inside square ABCD equals to either 25 pi over 3 square units, or in terms of numbers, it is equal to 26.18 square units. We finished with the first question. In the next step, I present to you the second question, and we'll solve the second question in 3 different methods. So in the drawing we have a quarter circle. Inside this quarter circle we have a small circle. We know that line segment CD equals to 8 units. We also know that angle ACD, this angle, equals to 90 degrees. And our mission is to find out the area, the value of the area of the green shape. Okay, the value of the area of the green shape. Okay, so we'll start with the first method, and here we will define the center of the small circle as J. We define the point of tendency of tangent CD with the small circle SE. We will define the point of tendency of tangent OB with the small circle SF. We will join points E and J together by a straight line. Point E is the point J is the center of the circle. Point E is the point of the circle itself. Therefore, EJ is the radius of the circle that we will define as R. EJ equals to R. And we have the radius EJ that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we will join points J and F together by a straight line. Point J is the center of the small circle, point F is the point of the small circle itself, therefore JF is the radius of the circle that is equal to R. And again, we have the radius JF that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. We also know in any quarter circle, point O is the center of the quarter circle, and this angle, it is always equals to 90 degrees, it is a right angle. So this angle is a right angle. And AO, in any quarter circle, AO is the radius of the quarter circle that we will define as capital R. Okay, AO equals to capital R is the radius of the quarter circle. So AO as a radius, it is absolutely a straight line. AO as a radius, it is absolutely a straight line. So this is a straight line, and if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees according to rule number 3, that the sum of the angles on one side of a straight line equals to 180 degrees. So which angles we have at this side of AO at point C, we have this angle that is equal to 90 degrees, plus the missing angle. In total, they must be equal to 180 degrees according to rule number 3. Therefore, the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on this side of the straight line AO at point C to 180 degrees. This angle must be also equal to 90 degrees. In the next step, from the center of the small circle, that is to say from point J, we draw perpendicular on CO. So here, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point J and CO as T. We will focus on quadrilateral, the small quadrilateral TJOF, this small quadrilateral. In this small quadrilateral, we have 1, 2, 3 right angles, that the sum of 3 right angles is 270 degrees. Therefore, the fourth angle must be also equal to 90 degrees in order to complete the sum of the angles in this quadrilateral to 360 degrees. This angle must be also equal to 90 degrees. Likewise, in the small quadrilateral CTJE, this small quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, therefore the fourth angle must be also equal to 90 degrees in order to complete the sum of the angles in this quadrilateral to 360 degrees. This angle must be also equal to 90 degrees. So we actually found out that angle EJF, this angle, it is equal to 90 degrees plus 90 degrees, that is 180 degrees. Angle EJF equals to 180 degrees. Therefore, you can conclude that angle EJF is a straight line. Any angle that is equal to 180 degrees, it is a straight line. So if angle EJF is a straight line, then line segment EJF is a straight line, and if line segment EJF is a straight line, then EF, line segment EF is also a straight line. So EF is a straight line, and if line segment EF is a straight line, it means that quadrilateral CEOF, this quadrilateral, is a rectangle. Quadrilateral CEOF is a rectangle because it has 4 right angles. Okay? And we know that the opposite sides of a rectangle are equal to each other. That is to say, side EF equals to side CO. Side EF equals to side CO. Okay, EF equals to CO. EF equals to CO. But we already found out that EF equals to R plus R, that is 2R. EF equals to 2R. And from this equation, 2R equals to EF equals to CO, we will derive that CO is also equal to 2R. CO is also equals to 2R. CO equals to 2R. CO equals to 2R. In the next step, we will join points O and D together by a straight line. Point O is the center of the quarter circle. Point D is the point of the quarter circle itself. Therefore, OD is the radius of the quarter circle that is equal to capital R. In the next step, we will implement the Pythagoras theorem on the right green triangle, triangle OCD. Okay. On the right green triangle, triangle OCD, by PT is abbreviation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle COD is OD, therefore the square of the hypotenuse is OD squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to CO squared plus CD squared. I repeat again, in the right hand triangle COD, according to the Pythagoras theorem, we get that OD square equals to CO square plus CD square. OD, therefore OD equals to capital R, therefore OD square is capital R square, that is equal to CO square. We already found out that CO equals to 2R, therefore CO square is 2R squared, that is 4R square, plus CD square. CD equals to 8 units according to what is given as the equation, therefore CD square is 8 squared, that is 64. In conclusion, according to equation number 1, we found out that R square, capital R square equals to 4R square minus 64. Here we subtract 4R square from this equation, equation number 1. And we get that according to equation number 1, R square, capital R square minus 4R square equals to 64. Okay, capital R square minus 4R square equals to 64 according to equation number 1. And what is the area of the green shape? It is very easy to see from the drawing that the area of the green shape will be equal to the area of the quarter circle minus the area of the circle itself. Okay, I'm writing down the area of the green shape. Will be equal to the area of the quarter circle minus the area of the small circle. Repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. So the area of the quarter circle will be equal to pi times capital R square over 4 minus the area of the circle, that will be equal to pi R square. So here we'll take pi over 4 as a common factor out of those two expressions. So pi over 4 is a common factor. So what is left from pi times capital R square over 4 after we took from it pi over 4 as a common factor? What is left is actually capital R square minus here what is left from minus pi R square after we took from it pi over 4 as a common factor. What is left? It is actually 4R square. Why? Because 4R square, it is actually 4R square. It is actually 4R square. Why? Because 4R square times pi over 4 equals exactly to minus pi R square. Okay, so in conclusion, we found out that the area of the green shape equals to pi over 4 times capital R square minus 4R square. But here we have already found out that capital R square minus 4R square equals to 64, therefore we can substitute capital R square minus 4R square by 64. We'll do it now and get that pi over 4 times 64 equals to the area of the green shape. 64 over 4 is 16, so in total this expression equals to 16 pi. So in conclusion, we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. So we finished in the first method. The next step I present to you the second method. To find out the area of this green shape, the value of the area of the green shape. We already found out in the first method that CO equals to 2R, AO is the radius of the quarter circle that is equal to capital R. In the next step, and here actually according to the first method, this angle it is also equal to 90 degrees, according to rule number 3 actually. So in the next step, we will complete the quarter circle to a circle. So I completed the quarter circle to a circle. We will extend the straight line CD by a straight line until it touches the circle. And we will define the touching point of the extended CD and the circle as point T. In the next step, we will extend the radius AO by a straight line until it touches the circle, and we will define the touching point of the extended radius AO and the circle as point M. We will join points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of the circle that is equal to capital R. Likewise, we join points O and T together by a straight line. Point O is the center of the circle, point T is the point of the circle itself, therefore OT is also the radius of the circle that is also equal to capital R. Here we extended the straight line DC, we extended this straight line DC by straight line. When you extend a straight line by straight line, the result that is dt must be also a straight line. That is to say, dt is a straight line, So if we focus on the lower side of the straight line DT at point C, here the sum of the angles must be equal to 180 degrees according to rule number 3. So which angles we have at the lower side of DC at point C? We have this angle that is equal to 90 degrees plus this, the missing angle. In total they must be equal to 180 degrees. Therefore the missing angle must be also equal to 90 degrees in order to complete the sum of the angles in the lower side of TT at point C to 180 degrees. This angle must be also equal to 90 degrees. Okay, so in the next step we will prove that those two right triangles can go into each other. So I write it down. We will prove that the right green triangle, triangle COD, is congruent to the right triangle, triangle OCT. So why those two right triangles can go into each other? First of all, TO and OD, they are both the radii of the big circle, therefore they are equal to each other. So I write it down. TO equals to OD, they are both the radii of the big circle, therefore they are equal to each other. In TO equals to OD equals to R. In addition, CO is a common side that belongs to both triangles, therefore CO equals to itself. CO equals to CO is a common side that belongs to both triangles. Actually, by proving that the hypotenuse and one perpendicular of those two right triangles congruent, we actually proved that those two right triangles can go into each other, and I will explain you why. It is enough, if you are talking about right triangles, it is enough to prove that the hypotenuse and one perpendicular of those two triangles congruent in order to prove that those two right triangles can go into each other. I will explain why. If, for example, we have triangle ABC, this is triangle ABC, a right triangle. And we have triangle DEF, that is also a right triangle. And they have the same hypotenuse, that is 5 and 5, and also one perpendicular also can go into those two right triangles. For example, this AB equals to 3 and DE is also equals to 3. Therefore, according to the Pythagoras theorem, BC, according to the Pythagoras theorem, BC will be equal to the square root of 5 square minus 3 square, that is 4. And then also EF will be also equal to the square root of 5 square minus 3 square, that is also 4. That is to say, when we have in two right triangles and the hypotenuse and one perpendicular congruent, then we can conclude that those two right triangles must also congruent to each other. Why? Because the third side of those two right triangles must also congruent. Here the third side is BC, that is equal to 4 units, and here also EF is also equal to 4 units. Okay, that is the reason that it is enough in two right triangles to prove that the hypotenuse and one perpendicular is congruent in order to prove that those two right triangles can go to each other. Therefore, we actually prove the right triangle COD congruent to the right triangle OCT according to side rule. Okay? And from the fact that those two right triangles congruent to each other, we will derive that DC equals to CT. DC equals to CT, and DC equals to CT according to the rule that corresponding sides and congruent triangles are equal to each other. Those two right triangles congruent to each other, therefore the two corresponding sides, that is to say DC and CT, must be also equal to each other. But it is given as the equation that DC equals to 8 units, so we can write here DC equals to 8, and from this equation 8 equals to DC equals to CT, we derive that CT is also equals to 8. CT is also equals to 8. Okay. Here point O is the center of the circle. Point M is the point of the big circle itself, therefore OM is the radius of the big circle that is equal to capital R. What is the value of AC? It's very easy to see from the drawing that the value of AC here AC equals to AO minus CO. AO minus CO. Repeat again. Line segment AC equals to AO minus CO. That is to say AC equals to AO, that is capital R, it is the radius of the big circle, minus CO, that is 2R. So in conclusion, we found out that AC equals to capital R minus 2R. In the next step, I present to you rule number 11, and we will implement rule number 11 in our drawing. According to rule number 11, if we have this circle, inside this circle we have chord AB that intersects with chord CD at point O. Again, chord AB intersects with chord CD at point O. Point O is the intersection point of those two chords. So, if this is the data that has been given to us, then the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Actually, you can implement rule number 11 in our drawing, because in our drawing we have chord AM intersects with chord TD at point C. Again, chord AM intersects with chord TD at point C. Right. I write it down. We have chord AM intersects with chord TD at point C. Therefore, here I put again, chord AM intersects with chord C, intersects with chord TD at point C. Therefore, according to rule number 11, we get that TC times CD, TC times CD equals to AC times CM, AC times CM. If it again, according to the rule number 11, we get that TD times CD equals to AC times CM. CD equals to 8, TC also equals to 8, therefore TC times CD is 8 times 8, that is 64, and it is equal to AC. AC equals to capital R minus 2R times CM. Here, what is the value of CM? It is very easy to see from the drawing that CM equals to capital R plus 2R. In conclusion, according to rule number 11, we found out that 64 equals to capital R minus R times capital R plus 2R. According to the algebraic identity that A plus B times A minus B equals to A squared minus B squared, we get that capital R minus 2R times capital R plus 2R equals to, here A will be equal to capital R and B will be equal to 2R. And these expressions are supposed to be equal to A squared minus B squared. That is to say, 64 equals to A squared. A squared is, A is capital R, therefore A squared is capital R squared minus B squared. B is 2R, therefore minus B squared is minus 2R squared. So in conclusion, we found out that 64 equals to capital R squared minus 2R squared is minus 4R squared. Minus 4R squared. So we found out that 64 equals to capital R squared minus 4R squared. 64 equals to capital R squared minus 4R squared. And what is the area of the green shape? The area of the green shape, it is equal to the area of the quarter circle minus the area of the small circle. Repeat again, the area of the green shape, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. Okay, so the area of the quarter circle equals to pi times capital R squared over 4 minus the area of the circle, that is pi R squared. So here we'll take pi over 4 as a common factor out of those two expressions. What is left from pi times capital R squared over 4? We took from it pi over 4 as a common factor. What is left is actually capital R squared minus pi R squared. What is left from minus pi R squared? We took from it pi over 4 is the common factor. What is left is actually minus 4r squared. Why? Because pi over 4 minus 4r squared equals to minus pi r squared. So I found out that the area of the green shape equals to pi over 4 times capital R squared minus 4r squared. But we have already found out that capital R squared minus 4r squared equals to 64. Therefore, we can substitute capital R squared minus 4r squared by 64. We'll do it now and get that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. We finished with the second method. In the next step I present to you the third method. We have already found out that CO equals to 2R. According to the first method, this angle equals to 90 degrees. The radius of the source circle equals to R. In the next step, we'll complete the quarter circle to a semicircle. We'll extend the radius AO by a straight line until it intersects the semicircle. And define the starting point for the extended AO in the semicircle as T. Point O is the center of the semicircle, point T is the point of the semicircle itself, therefore OP is the radius of the semicircle that is equal to capital R. Here we only found out that AO is also equal to capital R. So we know that we extended the radius AO, that is a straight line by a straight line. When you extend a straight line by a straight line, the result must be a straight line. That is to say, AT is a straight line. AT is a straight line that is equal to capital R plus capital R is 2R. So we can see the straight line AT is a chord that passes from the center of the semicircle, that is to say from point O to point O, and is equal to R. So any chord that passes through the center of the semicircle or circle must be the diameter of the circle or semicircle. So AT, that is equal to 2 times capital R, it is the diameter of the semicircle. Okay. AT is the diameter of the semicircle. We'll join points D and T together by a straight line. We'll join points A and D together by a straight line. So here we created peripheral angle ADT. Peripheral angle ADT rests on AT, that is the diameter of the circle. And we actually have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of a circle must be equal to 90 degrees. We can implement, so here we have peripheral angle A and B that rests on AB, that is the diameter of the circle, therefore peripheral angle A and B equals to 90 degrees. You can implement rule number 5 in our drawing. Because in our drawing we have peripheral angle ADT that rests on the diameter of this circle, that is AT. Therefore peripheral angle ADT equals to 90 degrees according to rule number 5. This angle equals to 90 degrees. In the next step, we will define angle ATD, this angle as alpha, and we define angle TAD, this angle as beta. We'll focus on the right triangle CDT, this right triangle CDT. This angle equals to alpha, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus alpha. Okay, this angle must be equal to 90 degrees minus alpha, but before that, we know that this angle in the right triangle ADT, this angle equals to 90 degrees. So if this angle equals to 90 degrees, it means that the rest other two angles must be equal to, in total, to 90 degrees. Why? Because 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. So here, alpha plus beta must be equal to 90 degrees. Alpha plus beta is equal to 90 degrees. If we subtract alpha from this equation, we get that beta equals to 90 degrees minus alpha, and if we subtract beta from this equation, we get that alpha equals to 90 degrees minus beta. Okay. Again, we will focus on the right triangle CDT. In this right triangle, this angle equals to alpha, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in the triangle. So I found out that this angle equals to 90 degrees minus alpha. But here, 90 degrees minus alpha is equal to beta. Therefore, we substitute here 90 degrees minus alpha by beta. Likewise, we'll focus on the right small triangle, triangle ACD. In this right small triangle ACD, right green triangle, this angle equals to beta. This angle equals to 90 degrees. Therefore, this angle must be equal to 90 degrees minus beta. But here, we already found out that 90 degrees minus beta equals to alpha. So I can substitute 90 degrees minus beta by alpha here. So, in the next step, we will prove that the right triangle ACD is similar to the right triangle, triangle CDT. Okay, the right triangle, triangle ACD is similar to the right big triangle, triangle TCD. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. So here, angle ADC equals to this angle, that is actually angle CTD. They are both equal to alpha, therefore they are equal to each other. In addition, those two angles, they are both equal to beta, therefore they are equal to each other. So here, angle CAD is equal to this angle, that is actually angle CDT. They are both equal to beta, therefore they are equal to each other. And finally, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So here, angle ACD is equal to this angle, that is actually angle TCD. They are both equal to 90 degrees, therefore they are equal to each other. So I actually found out that those two right triangles are similar to each other according to angle similarity rule. Triangle ACD is similar to triangle TCD according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that AC over CD, AC over CD equals to CD over CT. Repeat again. From the fact that the two right triangles are similar to each other, we will derive that AC over CD equals to CD over CT. So here, what is the value of AC? Here, we have already found out the value of AC. Here I write it here. AC, it is very easy to see from the drawing that AC equals to AO minus CO. AC equals to AO minus CO. Again, AC equals to AO minus CO. So AC equals to AO, that is capital R, minus CO, that is 2R. So in conclusion, we found out that AC equals to capital R minus 2R. Okay, so AC equals to capital R minus 2R over CD. CD equals to 8 units according to what is given as the question. Over CT. What is the value of CT? From the drawing it is very easy to see that CT equals to capital R plus 2R. Capital R plus 2R. In conclusion, we found out that according to equation number 1, capital R minus 2R over 8 equals to 8 over capital R plus 2R. Here we cross multiply this equation, equation number 1, and we get that according to equation number 1, 8 times 8 is 64, that is equal to capital R plus 2R times capital R minus 2R. That is to say, 64 equals to, we already found out that capital R plus 2R times capital R minus 2R equals to capital R squared minus 4R squared. Okay. According to the algebraic identity, that A plus B times A minus B equals to A squared minus B squared. And what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. Okay. And the area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle, that is equal to capital R square. So here we take pi over 4 as a common factor out of those two expressions, and we get that pi over 4, we did it, we already done it, so I will not repeat on it. Here we'll get capital R square minus 4R square. And we already found out that capital R square minus 4R square equals to 64, therefore we substitute capital R square minus 4R square by 64. And we get that pi over 4 times 64, it is the area of the green shape. 64 over 4 is 16, so in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. So we finished with the third method. The next step, I'll summarize the lecture. We'll start with the first question, of course. In the drawing, we have square ABCD, this big square. Inside square ABCD, we have a circle. Naturally also a right triangle here. Angle CBT equals to 30 degrees. Line segment PD equals to 5 units, and our mission is to find out the area of this circle. It is inside square ABCD. Okay, so here, first of all, we define the center of the circle as point O. We join points O and Q together by a straight line. Point O is the center of the circle, point Q is the point on the circle itself, therefore Q is the radius of the circle that is equal to R. We have the radius of Q that is known to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and P together by a straight line. Point O is the center of the circle, point P is the point on the circle itself, therefore P is the radius of the circle that is equal to R. And we have the radius of P that is known to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equal to 90 degrees. We know that all the angles inside the square are right angles, so inside square ABCD, all the angles, all those 4 angles, they are equal to 90 degrees, and especially this angle, it is equal to 90 degrees. So inside quadrangle PAQPO, inside this quadrangle, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of the 4th angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, the 4th angle must be also equal to 90 degrees. So we found out that quadrangle AQPO has 4 right angles, therefore quadrangle APOQ is a rectangle. And you know that the opposite sides of a rectangle are equal to each other. That is to say, AQ equals to PO. Or again, we start with AP equals to QO. Yeah. PO equals to NQ. PO equals to AQ. Okay, here PO equals to AQ. PO equals to AQ, but we know that PO equals to R, so we can write here that PO equals to R, and for this equation R equals to PO equals to AQ, we derive that AQ is also equals to R. Here AQ equals to R. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we get that AP equals to QO. AP equals to QO. AP equals to QO. AP equals to QO, but QO equals to R. And for this equation, R equals to QO equals to PA, we will derive that PA is also equals to R. Here, PA is also equals to R. So we found out that quadrangle AQPO is not a rectangle but a square because all of its sides are equal to each other, they are equal to R. And you know that all the sides in square ABCD are equal to each other, that is to say side AD equals to side AB. AD equals to AB. Here, AD equals to AB. What is the value of AD? AD equals to R plus 5. And AD equals to R plus BQ. AD equals to R plus 5 and AB equals to R plus BQ. So here we subtracted R from this equation and found out that BQ equals to 5. BQ equals to 5. Then I presented to you rule number 2 and implemented rule number 2. Now drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point P. From point P we have tangent PA and tangent PB. According to rule number 2, PA equals to PB. We can implement rule number 2 in our drawing, because in our drawing we have the common external point B. From the common external point B, we have tangent BQ and we have tangent BS. And according to rule number 2, they are equal to each other. Here, BQ equals to BS according to rule number 2, but we have already found out that BQ equals to 5. So for this equation 5 equals to BQ equals to BS, we know that BS is also equals to 5. Here BS equals to 5. Then we join points S and Q together by straight line. In this way we created a triangle QBS. In triangle QBS, what is the value of this angle? This angle equals to 90 degrees plus 90 degrees minus 30 degrees, that is 60 degrees. And those two sides are both equal to 5 units, therefore they are equal to each other. Therefore, we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of equal sides must be equal to each other. So if one angle is alpha, then the other angle must be also equal to alpha. So those two angles are both equal to alpha. This angle equals to 60 degrees, therefore the rest two angles must be equal to 120 degrees. That is to say, alpha plus alpha must be equal to 120 degrees. Alpha plus alpha is 2 alpha, that is equal to 120 degrees. We divided this equation by 2 and found out that alpha equals to 120 degrees over 2 is 60 degrees. So those two angles are both equal to 60 degrees. Therefore, triangle BSQ is an equilateral triangle because all of its angles are equal to 60 degrees. And in equilateral triangle, we know all of its sides of an equilateral triangle are equal to each other. So side BS equals to 5, side BQ equals to 5, therefore side ASQ must be also equal to 5. Then we join points O and S together by a straight line. Point O is the center of the circle, point S is the point of the circle in the center. For OS is the radius of the circle that is equal to R. We have the radius OS that is known to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Then I copy quadrangle SOBQ in a new page and we analyze triangle SOBQ. That is quadrangle SOQ QBOS that I copied from the original drawing. This quadrangle, we have two right angles and this angle equals to 60 degrees. And we know that the sum of the angles in any quadrangle is 360 degrees, therefore 360 degrees minus the sum of those three angles must be equal to the size of the missing angle. So 360 degrees minus 90 degrees minus 90 degrees minus 60 degrees is 120 degrees. So the size of the missing angle is 120 degrees. This angle equals to 120 degrees. Then I presented to you the law of cosines, and we implemented the law of cosines in the green triangle. According to the law of cosines that is for in any triangle, if we have triangle ABC, side AB equals to A units, side AC equals to B units, and side BC equals to C units, and the angle between side AB and side AC is theta, then according to the law of cosines, C square equals to A square plus B square minus 2 times A times B times cosine theta. We implemented the law of cosines in this triangle QOS, I copy triangle QOS of the original drawing, and according to the law of cosines, in triangle QOS, we get that 5 square equals to R square plus R square minus 2 times R times R times cosine 120 degrees. Okay, so 5 square is 25, R square plus R square is 2R square, minus 2R times R is minus 2R square, cosine 120 degrees is minus R, minus 1R. So we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and the minus times minus is plus. So in conclusion, we found out that 25 equals to 2r squared plus r squared. 2r squared plus r squared is 3r squared. So in conclusion, we found out that 25 equals to 3r squared. We divided this equation by 3 and found out that r squared equals to 25 over 3, and the area of any circle is pi r squared. But we have already found out that r squared equals to 25 over 3, therefore we can substitute r squared in this equation by 25 over 3. We did it, and we got that the area of the circle equals to pi times r squared. R squared is 25 over 3, so in conclusion we found out that the area of this circle is equal to either 25 pi over 3 square units, or in terms of numbers it is equal to 26.18 square units. We finished with the first question, then I presented to you the second question, and we solved the second question in 3 different methods. Okay, so here we have a quarter circle. Inside the quarter circle we have a small circle, and our mission is to find out the area of the grid shape. Okay, so we defined the center of the small circle as J. We define the point of tendency D with this small circle as A. We define the point of tendency of tangent OB with this small circle as F. We join points J and D together by a straight line. JE is the radius of the circle. We join, and we have the radius JE that is going to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. We join points J and F together by a straight line. JF is the radius of the circle. We have the radius JF that is going to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Then this angle equals to 90 degrees because of the fact that AOB is a quarter circle. Therefore, this angle equals to 90 degrees, and point O is the center of the quarter circle. Here we have AO is the radius of the quarter circle that is equal to capital R. So AO as a radius is a straight line, and we know that the sum of the angles on one side of the straight line is equal to 180 degrees. So if we focus on this side of the straight line AO at point C here, this angle equals to 90 degrees, therefore the missing angle must be also equal to 90 degrees. In order to complete the sum of the angles on this side of AO at point C to 180 degrees, this angle must be equal to 90 degrees. Then from point J we go perpendicular on CO. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. So inside quadrangle CETJ we have 1, 2, 3 angles. Therefore, the fourth angle must be also equal to 90 degrees. Inside quadrangle TJOF we have 1, 2, 3 angles. Therefore, the fourth angle must be also equal to 90 degrees. So here angle CTO, this angle equals to 180 degrees. Therefore, line segment CTO is a straight line. Here angle EJF, this angle equals to 90 degrees plus 90 degrees, it is 180 degrees. Therefore, angle EGF that is equal to 180 degrees, it is a straight line. Therefore, line segment EGF is a straight line, and therefore line segment EF is also a straight line. If line segment EF is a straight line, it means that quadrangle CEOF is a rectangle. Why? Because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, CO equals to EF. CO equals to EF, but we have only found out that EF equals to R plus R, that is 2R. And for this equation, 2R equals to EF equals to CO, we will derive that CO is also equals to 2R. Here, CO equals to 2R. Okay? Then, we join points O and D together by a straight line. Point O is the center of the quarter circle. Point D is the point of the quarter circle itself. Therefore, OD is the radius of the quarter circle that is equal to capital R. Then we created the Pythagoras theorem on the right green triangle, triangle COD. According to the Pythagoras theorem, DO square equals to CO square plus CD square. Repeat again, DO square equals to CO square plus CD square. DO is capital R, therefore DO square is capital R square. CO is 2R, therefore CO square is 2R squared, that is 4R square, plus CD square. CD is 8, so CD square is 8 squared, that is 64. In conclusion, we found out that capital R square plus equals to 4R square plus 64. We subtracted 4R square from this equation. We found out that capital R square minus 4R square equals to 64. What is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. Again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle equals to pi times capital R square over 4, and the area of the circle equals to pi R square. We took pi over 4 as a common factor out of those two expressions. What is left from pi times capital R square over 4 after we took from it pi over 4 as a common factor? What is left is actually capital R square. What is left for minus pi R square after we took from it pi over 4 as a common factor? What is left is actually minus 4R square. And here we already found out that capital R square minus 4R square equals to 64, therefore we can substitute capital R square minus 4R square by 64. We did it, and we got that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, so this expression in total equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. We finished the first method, then I presented to you the second method. In the second method, here we already found out that in first method that CO equals to 2R, and we already found out that this angle equals to 90 degrees in the first method. We completed the quarter circle to a circle. We joined points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of the circle that is equal to capital R. Then we joined points O and T together by a straight line. Again, point O is the center of the circle, point T is the point of the big circle itself, therefore OT is the radius of the big circle that is equal to capital R. And again, we actually extended the straight line DC by a straight line, therefore the result DT must be also a straight line. So if we focus on the lower side of the straight line DT at point C, here the sum of the angles must be equal to 180 degrees, according to rule number 3. So this angle equals to 90 degrees, therefore the this angle must be also equal to 90 degrees. So here we created here two right angles, triangle OTC and triangle COD. And we proved that those two right angles can go into each other. Why they can go into each other? First of all, CO is a common side that belongs to both triangles, and we also have the hypotenuse OD equals to the hypotenuse OT. They are both the radii of the big circle, therefore they are equal to each other. Okay, so here we actually prove that those two right triangles can go to each other according to side rule. Okay, and from the fact that those two right triangles can point to each other, we will derive that CD equals to CT, but CD equals to 8, therefore CT also equals to 8. Then we implemented here rule number 11. According to rule number 11, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay, so here we can implement rule number 11 in our drawing. Why? Because in our drawing we have chord AM that intersects with chord DT at point C. Again, chord AM intersects with chord TD at point C. Therefore, according to rule number 11, we get that TC times CD equals to AC times CM. Again, TC times CD equals to AC times CM. Repeat again. TC times CD equals to AC times CM. TC equals to 8. CD also equals to 8, therefore TC times CD is 8 times 8, that is 64. AC equals to capital R minus 2R, and CM equals to capital R plus 2R. So in conclusion, we found out that 64 equals to capital R minus 2R times capital R plus 2R. So 64 equals to capital R minus capital R square minus 2R square. According to the algebraic identity that A plus B times A minus B equals to A square minus B square. So 64 equals to capital R square minus 4R square. So again, 64 equals to capital R square minus 4R square. And the area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle, that is pi R square. We took a pi over 4 as a current factor. Inside the brackets we left only with capital R square minus 4 R square, but we already found out that capital R square minus 4 R square equals to 64, therefore we substituted capital R square minus 4 R square by 64 and found out that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, so in total this equation equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. Then I presented to you how to find out the area of the green shape according to the third method. Again, here we have already found out that CO equals to 2R in the first method. We have already found out in the first method that this angle equals to 90 degrees. We completed the quarter circle to a semicircle. Here we extended the radius AO by a straight line. Point O is the center of the circle, point T is the point of the circle itself, therefore OT is the radius of the semicircle, that is equal to capital R. We extended the straight line AO by straight line, therefore AT is a straight line that passes through the center of the semicircle, therefore AT is the diameter of this semicircle. We join points C and D together by a straight line, we join points D and A together by a straight line. ADT, peripheral angle TDA or ADT, rests on AT, that is the diameter of the circle, and we have rule number 4, rule number 5 that says that any peripheral angle that rests on the diameter of the circle must be equal to 90 degrees. If peripheral angle A and B rests on AB, that is the diameter of the circle, therefore peripheral angle A and B equals to 90 degrees. This peripheral angle ADT that rests on the diameter of the circle equals to 90 degrees. Okay, then we define this angle as alpha, we define this angle as beta, so in the right triangle ADT, this angle equals to 90 degrees. Therefore, the rest other two angles, that the sum of the other two angles must be equal also to 90 degrees. Why? Because 90 degrees plus 90 degrees, it is 180 degrees. That is to say, alpha plus beta must be equal to 90 degrees. Here we subtracted alpha from this equation and found out that beta equals to 90 degrees minus alpha. Then we subtracted beta from this equation and found out that alpha equals to 90 degrees minus beta. Then we focused on the right angle CDT. This angle equals to alpha. This angle equals to 90 degrees. Therefore, this angle must be equal to 90 degrees minus alpha. But 90 degrees minus alpha is beta. So we substituted 90 degrees minus alpha by beta. Then we focused on the small green right triangle, triangle ADC. Here, this angle equals to beta. This angle equals to 90 degrees. Therefore, this angle must be equal to 90 degrees minus beta. But 90 degrees minus beta is alpha. So we substituted 90 degrees minus beta by alpha. Then we proved that the right green triangle, triangle ADC, is similar to the right green triangle, triangle CDT. Triangle CDT is similar to triangle ADC. Why those two triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to beta, therefore they are equal to each other. And finally, those two angles are equal to 90 degrees, therefore they are equal to each other. So I found out that triangle ADC is similar to triangle TCD according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that AC over CD equals to CD over CT. Again, AC over CD equals to CD over CT. AC equals to capital R minus 2R. CD equals to 8. And CT equals to capital R plus 2R. In conclusion, found out that capital R minus 2R over 4 equals over 8 equals to 8 over capital R plus 2R. We first multiplied this equation and found out that 64 equals to capital R plus 2R times capital R minus 2R. So 64 equals to here capital R plus 2R times capital R minus 2R equals to capital R square minus 4R square. So we found out that according to equation number 1, 64 equals to capital R square minus 4R square. Then, what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle equals to pi times capital R square over 4, and the area of the small circle equals to pi R square. We took pi over 4 as a common factor out of those two expressions, so inside the brackets we left only with capital R square minus 4R square. But capital R square minus 4R square equals to 64. Yeah, capital R square minus 4R square equals to 64. So we substituted capital R square minus 4R square in this equation by 64 and found out in total, in conclusion, that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16. So in total, this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. Okay, thank you very much.